Okay, good morning, everybody. It's my pleasure to introduce our first plenary speaker this morning, James Lee. James is a professor of computer science at the University of Washington, Seattle. And in case you hadn't noticed, Washington really swept the plenaries this year. This is the second of 3 Washington plenaries this week. James got his PhD in 2005 at Berkeley in computer science, and before joining Washington, he did some postdoctoral work at the Institute for Advanced Study in Princeton. James is a 2017 winner of a Simons Investigator Award, and among his other awards and honors, there's an NSF Career and a Sloan. James has broad research interests in theory of computation, algorithms, complexity, and probability. And the title of his plenary talk is Unimodular, Uniformization, and Random Walks. So let's welcome James.
Yeah, it's a pleasure to be here. Thanks for the invitation. As was mentioned, I spend a lot of time as a computer scientist, so it wasn't clear to me whether I should talk about computer science or probability. So I don't know if I'm if I'm disturbing the organizers diversity of topics, but I'm going to talk about it's a pure probability talk. Okay, so the talk is about some families of objects that we've seen already a lot this week. Right, so in geometry, there's this long history of an interplay between symmetry and geometric properties, and then, but in lots of statistical models where you don't have geometric symmetry, you still have there is still symmetry in law. So maybe one of the most basic examples is say bond percolation on a transitive graph. So if you remember Smirnov's talk from Monday, so here you are sitting in a point. Well, let's see. Maybe that's there we go. Here you are sitting at a point of the integer lattice. You do some percolation, and obviously there is if I sample here, there is no quenched symmetry. Like things are very asymmetric, but in a annealed sense, of course, I mean things are symmetric in the sense that if I cannot distinguish which point I'm at by looking at the law of the geometry around me. Okay, so my talk is about some tools to say interesting things about these kind of stochastically homogeneous geometries, and I will give some. I mean, you'll see soon some formal definitions. My 2 running examples are going to be, let's say, critical percolation on the square lattice, and uniformly random triangulations of the 2-sphere. So let me just say, so here is another model that has this sort of stochastic homogeneity. Take all of the triangulations of the 2-sphere sort of up to combinatorial equivalence, choose a uniformly random one. Those things obviously have been extremely well studied. And I mean, here's a picture of one that if you can look, and you can find thousands of such beautiful pictures. They have all kinds of properties that are either known to be true or conjectured to be true that are surprising and very appealing. And so I will talk about some tools to deal with these things. One of the features of those models, as many experts in the room know, is that especially at criticality, they exhibit some kind of fractal behavior. So some sort of non-trivial, multi-scale, interesting geometry at every scale. And so that will be the case today. There is a beautiful theory of analysis on fractals, which especially in what's called the strongly recurrent case gives you the ability to make predictions about, say, certain notions of dimension. Let me just give this setup now. So the definitions are going to come here in just a second. In fact, this slide, that was it for the part that you could miss at the beginning of the talk. So this slide is going to have definitions that are key the whole time. But let me state some intuitive phenomenon and then tell you the definitions behind it. So if a graph has uniform, say, d-dimensional polynomial growth, so the balls in the graph grow at some polynomial rate. And you have some very strong effective resistance bounds. So the effective resistance between pairs of vertices is up to constant factors, power of the graph distance. Then the following intuition roughly holds, that if you start random walk at some point x, then before that random walk escapes a large ball, it will roughly sort of, mix on a smaller ball. Okay, this is okay. So here are the definitions. dg is the path distance in the graph. This bg throughout the talk, this is the ball of radius r in the graph distance around the vertex x. And uniform polynomial growth means that that the size of balls is trapped between the constant times r to the d for some d, and then this is d-dimensional growth. Okay, so that's so this is what this allows you to do is, for instance, confirm various exponents you might predict. So if you look at the connection between effective resistances and heating times in a graph, and you look at the size of the balls according to this growth assumption, then you might predict, for instance, that the speed of the random walk, the expected displacement from your starting point after n steps, grows like this, n to the 1 over d plus beta. And for instance, the return probabilities. This thing is slowly dying. Maybe. All right, I'm gonna reserve it for clicking because and the return probabilities sort of satisfy what you might expect. Let's just go through it real quick. If after n steps you expect to be at about this distance from your starting point, and this intuition holds that you've roughly mixed on this ball, then the ball of this radius has n to the d over d plus beta points because of this polynomial growth assumption. And so then you would expect that the probability that you're at your starting point, if indeed this intuition is true, decays like this, which is just 1 over the size of the ball that you expect to sort of have weakly mixed over in that time. Okay, so the main point is just that if you make strong assumptions about the compatibility between the spectral or potential structure of the graph and its intrinsic geometry, then you can make strong conclusions about various exponents. These are sometimes called the Einstein relations, for better or worse. And okay, so this is a setting in which one understands things. And the problem is that in these stochastic settings, like the examples I gave earlier, well, certainly things like this don't hold almost surely, but and even if some variants of them do hold, these implications might not hold, and even if some variants of them do hold, it might be very hard to prove that. So the goal today is to give a tool that is able to sort of that is able to, for instance, get control on some level of control on these quantities, like the rate of escape of the random walk, or the spectral dimension, which is related to the decay of the return probabilities, without having this strong setup. Okay, so let me just give an example of a classical setting and then some stochastic analog. Suppose you have a vertex transitive graph, so say the Cayley graph of a group, and you know that it has at most polynomial growth. So then a simple conclusion you can make is that the random walk has diffusive speed. So after n steps, the displacement from the starting point is roughly square root of n. I mean, in fact, you can say much stronger things. For instance, work of Habish and Solov-Kost, because you can really nail down the heat kernel and sub-Gaussian decay and everything. But these theorems are all based on the structure theory of such graphs, which go back to essentially like Gromov's theorem for groups of polynomial growth. So they're based on the fact that you can classify vertex transitive graphs of polynomial growth. Suppose now that let's go to the stochastic setting and see what some set of assumptions might look like. So in everything we talk about, our random geometry is going to be a random rooted graph. And then whenever xn will just denote simple random walk. And if I don't specify the starting point, then I'm always starting it at the root of this random graph. And then you say that this random graph, so this is a random rooted graph, you say that it's stationary if when you take one step of the random walk from the root, you end at a random rooted graph with the same law. Okay? So this is a very natural condition on, say, random rooted graphs that say that you have this kind of homogeneity along the random walk. You reroute the graph along the random walk, the law is the same. Okay, and here's an example of something that one can, of an analog one can try to prove in this setting, that if you have a stationary random graph that has annealed polynomial volume growth, so you have a bound on the expected size of balls in the graph, then there exists a sequence of times such that at those times, the speed of the random walk is at most diffusive. Okay, so this is a theorem we proved with Shirshendu, Ganguly, and Yuval Paris. And well, one of our motivations for this theorem was related to, there's a beautiful work here that shows a relationship between the speed of random walks and the space of harmonic functions. So this has some non-trivial potential theory content. But what I really want to focus on, all right, something fancy, is that, I mean, this is, like things become much more difficult in the stochastic setting. So for instance, passing to this subsequence of times is necessary. So there are times at which the random walk actually goes faster than this. And I want to point out that this result like this was actually previously unknown, even if you take random subgraphs of z to the d. Sometimes people find that surprising because they remember a paper of Keston that proved that the random walk on a stationary random subgraph of z to the d in a different language, but essentially this is subdiffusive. But Keston's subdiffusive bounds are in the Euclidean distance. So for instance, famously, Keston proved that random walk on large percolation clusters at criticality in the square lattice is subdiffusive, so the speed is asymptotically less than square root of n. But that's in the Euclidean distance, and if you care about the graph distance, or what physicists sometimes call the chemical distance, then subdiffusive speed in the Euclidean distance doesn't tell you something. I've sort of indicated that here by drawing here's a pair of points, and I've drawn the shortest path. Obviously, the Euclidean distance is small, but the graph distance is quite large. So, and now just as a forward pointer, what I want to say is that sort of the techniques of this first theorem I stated here, for concrete reasons, cannot hope to prove, say, subdiffusivity for random walk on large percolation clusters, because they're working in the wrong geometry. And this is a forward pointer. We'll see it in a couple of slides. That what we're going to do, the main point of the talk, is to consider a random change of metric on some, say, stationary random graph, where basically you deform the geometry so that it's more amenable to analysis, and then you do the analysis there. So that's the sketch of the talk. I want to before we go on to that, sort of give one more example. Like everything in the talk is along these two lines. One set of examples is related to this IIC, so critical percolation clusters in the 2D square lattice, or the square part is not so important here. And on the other hand, these random triangulations. So let me remind people, or tell people for the first time, about this, what I will call throughout the talk a distributional limit of graphs. So if you have a sequence of random rooted graphs, then I'll say that it converges distributionally, or in the Benjamini Schrum sense, to a random rooted graph G rho if the local views around the root all converge in law. So if for every radius the law of the balls of radius r around the root convert in the graphs along the sequence converge to the law of the ball around the root in the limit graph, where I consider balls up to rooted isomorphism. Okay, so this is a notion, very well studied notion of a very well studied topology on the space of random rooted graphs, and I'll be primarily interested when I talk about unimodular graphs in this setting where we're considering a sequence of finite graphs. So each of these graphs is finite. The root is chosen uniformly at random among the vertices. And then the object I'll care about is this limit object, which is the distributional limit of those things. Okay? And that thing is unimodular. I told you in this weird way because I decided that the mass transport principle has too many quantifiers for a talk. So, I mean, obviously not any setting, but okay. But in general, one defines unimodularity in terms of a mass transport principle. But for everything we are going to say, you can think about unimodularity as just distribution limits of finite graphs. It's a famous open question whether, in generality, unimodular random graphs are all limits of finite graph sequences. But in the setting that we care about, which is going to be graphs of sub-exponential growth, it's true. And I think that even if it's the first time you saw it, this notion of a stationary random graph was very natural. So let me just say that unimodular random graphs, at least in the setting we're going to discuss here, are just stationary random graphs where you change the law. Basically, you take a stationary random graph and you make it, if the degree of the root is d, you make it 1 over d times less likely to sample that random rooted graph. Of course, you have to rescale, so you have to maintain a probability measure. But basically, it's just a transformation that takes, like if you think about a finite graph, it takes the stationary distribution to the uniform distribution. Just two sort of different views of the same kind of object. Okay. Benjamini and Schramm in 2001 proved the following about limits of finite planar graphs. So if G rho is a distributional limit of finite planar graphs, and all of the degrees are uniformly bounded, then the graph is almost surely recurrent, which means that the random walk returns to its starting point infinitely often, almost surely, or just almost surely, period, it returns to its starting point. And the reason they looked at this question was coming, as many things here, from the physics literature, where in this area of the geometry of random surfaces, or what they call their quantum geometry, they were doing many simulations on these random triangulations and making many predictions. And Oded and Itai wanted to see if they could confirm some of those predictions. And one of those predictions is the random walk should be recurrent, with the only problem here being that their theorem holds when the vertex degrees are uniformly bounded, but they are not uniformly bounded in random triangulations. So it took a while to reconcile this, to sort of fix this problem. But Uri Gurel-Gurevich and Asaf Nachmias in 2013 showed that there is a generalization of the Benjamini-Schramm theorem that actually applies if the tails of the degree of the root go down sufficiently fast. Okay, so if it has exponential tails, then you get the same conclusion. The graph is, again, almost surely recurrent. And it's known that the degrees in UIPT satisfy this property. Okay, so before we go on to the main topic, I just want to use this as a chance to ask a question that I asked myself, and also Itai has been asking a lot longer. Like, how important is unimodularity in this result? Okay, so what I mean by that is the following. Here again is a picture of this UIPT. I will use the picture to now. So to describe something. But okay, so one very beautiful thing that's known about these graphs is that they have this fractal character. For instance, while they're topologically planar, they're two-dimensional, the volume growth is quartic. So the balls grow at rate about r to the fourth as r goes to infinity. And on the other hand, this graph has very small separators. So if you take the ball of radius r, then, I mean, you can see here, you can see here sort of, there are these, actually at every scale, there are these cut points that sort of separate large chunks of the graph with, no, they're not cut points, by the way, they just look like that on the slide, but small sets that separate large chunks of the graph off. And Benjamini and Papasoglu proved that actually the second property just follows from planarity and uniform polynomial growth. Okay, so what you could ask is, for instance, maybe unimodularity is not essential here. Like for maybe that's not the essential property of UIPT that's being used. Maybe it's just once you have polynomial growth that's bigger than quadratic, say, then you get this sort of this property that there are these very small, unusually small cuts in the graph. Maybe this is enough to get recurrence. And so in fact, Itai conjectured that every planar graph with uniform polynomial growth is recurrent. And an interesting fact is that this is false. So for every epsilon, there are planar graphs with, it doesn't say here, but, oh, of course, yes, it doesn't say here because it's false. Yeah, for every epsilon, there are transient planar graphs with growth r to the 2 plus epsilon. Okay, so in that sense, the unimodularity assumption is it's being used in an interesting way here. Like it's false just to say that the graph has this unusual dimension of volume growth and that disagrees with its topological dimension. Okay, so good. Those are our two examples. People like, people like that. We can do it one more time. Okay. And I want to say here again, similar families of examples show that even in a unimodular setting, this kind of strong recurrence can fail. And in fact, I'll talk about it at the end. I mean, the random walk, for instance, in these examples spreads out more like this. So it definitely doesn't spread out in this way that the conclusion holds. I mean, one can establish that the effective resistances are not as one would like for this to hold. But indeed, it happens that the random walk spreads out in this very funny way. So I'll come back to this at the end. Now we want to get on to, okay, so we don't have this tool at our disposal to be able to prove things about these spectral properties like rate of escape, spectral dimension. I'll define spectral dimension soon. Okay, so what are we going to use instead? So deformations of the graph geometry. So our deformation is going to look like this. It's going to be a non-negative vertex weight omega. And then given such a vertex weight, we can define this weighted graph distance. So just distance between two vertices is just the shortest path length. But now the length of a path is weighted by this omega, right? Okay, people nodding are on board with that at least. I'm only going to consider, so this is I have a random rooted graph. The weight will also be random. I only want to consider random weights where this triple is sort of all unimodularly compatible. So one way to say that is that in the sense of, say, Aldous Lyons, this is unimodular as a Mark network. But it's perhaps easier just to go back to the stationary setting where you bias by the inverse of the degree of the root. And in the stationary setting, it just means that when I consider this triple, the law is invariant under rerouting along the random walk. Okay, so the point is, I mean, this is a random weight that's coupled perhaps to the root. It shouldn't somehow depend in some very strong way on what the root is. Okay, and let's say that this weight is normalized if if the expected square is 1. Okay, so. You can think about this if you want to think about some analogies with geometry. This is basically saying that the area of this weight is 1. Okay, this is the hardest definition to parse in a talk. I want to define the extremal growth rate of a unimodular random graph as, okay, let me say it in words. Look over all normalized unimodular random weights. I want the one where okay, so this b sub omega, this is the ball not in the graph distance, but in this weighted graph distance. And over all such normalized weights, I want to find the one where the growth of these b omega balls is sort of the polynomial growth is as small as possible. That's what I'm trying to capture here. There's a bunch of crap with an essential supremum and so on. Let me just say that what it means. It's basically, I want there to be a function f of r so that almost surely the size of the r ball in the omega metric around the root is at most f of r. And f of r goes to infinity like r to the d for some d. The point being here that this upper bound on the size of a ball is not an expectation, it's an almost sure upper bound. Okay? That shouldn't trouble you too much because the point is you have this weight. So for instance, if a graph has unbounded degrees, and you just take this weight to be identically 1, then the metric you get will just, of course, be the graph metric back. These will be graph balls, and then those balls, if the degrees are not uniformly bounded, then in this sense there will be no bound on the growth rate because there's no almost sure bound even on the sides of a ball of radius 1. But you have this weight. So for instance, you can fix this problem by you could put large weight on high degree vertices, and then in order to actually get all of their neighbors into the ball would have to be quite large. Okay, so because you have this option of sort of, putting this weight wherever you want, this almost sure upper bound is not crazy. Okay, so this is just a definition repeated. And now let me tell you the spectral dimension of a graph. And by the way, there are a bunch of limits. They may not exist. So everything I say is that when the limit exists, and if not, you can define upper dimensions and lower dimensions and have fun deciding how to LaTeX everything. Yeah, the spectral dimension of the graph is the following limit if it exists. And again, instead of talking about it, let me just say what it is. The spectral dimension is d sub s if the return probabilities to a fixed vertex decay like n to the minus ds over 2. So this is a notion of dimension that physicists like because, well, there are various reasons, but in particular, it's what you might call reparameterization invariant. So it's sort of like some kind of intrinsic notion on the geometry. And here is a first sort of non-trivial theorem about how you can use these weights. If you have a unimodular random graph and the degree of the root isn't too crazy, so it has so negligible here means that just that the tails of the degree go to 0 faster than any inverse polynomial. So like exponential tails certainly satisfy this, but it's much weaker. Then almost surely the spectral dimension of the graph is at most this growth rate. And there's something I should have said here when I'll say it now. This is an abuse of notation. This is an abuse of notation because this is not a random variable. This is this extremal growth rate is a function of the law of the random graph. I've just, in order to avoid many parentheses, I wrote it like this. But whereas this spectral dimension here, this is a random variable. Okay, so that's sort of like so that's what the almost surely refers to. If you take a unimodular random graph with extremal growth rate at most d, then almost surely G has spectral dimension at most d. Okay, so it's not clear what content this has because you haven't seen anything that has you haven't seen any bound on the extremal growth rate. So let me tell you another theorem that if a graph is a distributional limit of finite graphs that can be represented in a d-dimensional space, so let's say sphere packed in a Euclidean d space, then this extremal growth rate is at most d. Okay, so let me just be clear about what I mean by sphere packed. So I don't put any bounds on the radii of the spheres or the degree of the number of spheres touching each other. I just want it to be that the graph is the tendency graph of interior disjoint spheres in RD. Okay, like so. Here's two pictures of those things, and this is quite general, by the way. I mean, you can allow bounded overlaps, and you can allow shapes that don't look like balls but are just trapped between balls of similar radii, and so on. And one of the corollaries of this, I mean, just in the d equals 2 case, is that many well-studied random planar models where the spectral dimension was conjectured to be 2, well, if the spectral dimension exists, if this limit exists, it's almost surely at most 2, simply because all such planar graphs by the Kobe-Andreev-Thurston admit circle packings in the plane, and therefore their extremal growth rate is at most d. And for a large subset of these, I'll come back to this a little bit later as well, a large subset of these models, it has now been established by Gwynn and Miller that, in fact, the spectral dimension is also at least 2, almost surely, and therefore this pins down the spectral dimension, okay, of those graphs, the rate of decay of the return probabilities. So let me, I will show you soon an example of constructing such a weight explicitly, but let me just give you a flavor of what goes on in the arguments. It's not a straightforward how you prove this, like how you get this random weight. I will just say that basically it involves a quantitative understanding of accumulation points. So as long as the packing is sort of you stay away from accumulation points, basically you can rescale the Euclidean geometry according to the according to the measure on the graph and according to the number of vertices in, say, some cell, you can rescale in an appropriate way to get this. And accumulation points are really the tricky part, where the geometry is kind of running away from you, like here. At least morally, the reason that you can do this is that Benyamini and Schramm prove that if you have a distributional limit of, say, finite planar graphs, then almost surely the circle packing has at most one accumulation point. So there's basically at most one source of problems, and because you have this weight where it's only required to be bounded in L2, you can say if there's only one source of problems, you can devote all the attention of this weight to the accumulation point. Okay, that wasn't very. We'll see a construction of a weight soon. I agree that wasn't very illuminating. But let me tell you the proof of. Let me tell you again the intuition behind the proof of this theorem, that the spectral dimension is almost surely bounded by this growth rate. It's just you take what we said for strongly recurrent graphs, that the random walk basically kind of mixes on an R ball before it leaves the constant times R ball. And that's false. But at least in an average sense, the random walk, it is true if you look at balls in this omega metric. So the random walk mixes on this omega ball before it leaves a ball constant times larger. And then if you know that this ball has at most R to the D points, then that gives you upper bound on that gives you a lower bound, on the return probabilities, because you roughly mix on this set of size R to the D. I guess it's not. I guess I should have written here something more, which is which is, I guess there is one thing missing for this to make sense, which is in fact that if you do the random walk for t steps, it's also the case that the expected distance in this omega metric is square root of t. So if you combine those two things together, then you can relate the return probabilities to the, then you can understand what happens in terms of the time of the random walk. So if you run the random walk for t steps, then basically you roughly mix on a ball of size square root of t in this omega metric, not in the original metric. Okay, so it just changes the geometry so that kind of the intuition, what you would have liked to hold, still holds. Let me just, this is a bit, maybe, let me not, so let me just say here that if this, you can also use this for more precise things. This spectral dimension has some polynomial error, but if you care about transients versus recurrence, then like even the logarithmic terms will make it so you can't study those things. This method allows you to really, for instance, pin down the assumption on the degrees of the root that give you recurrence in these models. So I said that Gorelgarevich and Nachmias showed that exponential tails suffice. It turns out that even somewhat slower than exponential tails suffice. So you can give a precise characterization that's tight. I want to show you how to construct such a weight, because otherwise we don't have any intuition here. So let me go on to talking about the rate of escape. And I mentioned this already. So just for the ease of stating this theorem, let me state it in terms of stationary random graphs instead of in terms of unimodular random graphs. But if you again take sort of one of these random weights, then here is something you can show, that the random walk is, the speed of the random walk is almost at most square root of n, not in the graph metric, but in the omega metric. Okay, so for it doesn't, sort of if you take a normalized weight, so this expectation is 1, then after n steps, your distance, this says your distance is at most constant times square root n log n. And right, so it expresses this fact that the random walk is at most diffusive in this omega distance. And if you really want, say for the case of planar graphs, you can get rid of this log n. So in the case of planar graphs, it's really at most diffusive. And okay, so these theorems, I mean, they are using like non-trivial machinery. So the theory of Markov type that was introduced by Keith Ball in the setting of nonlinear geometric functional analysis, and then sort of used in this form for the first time, in a setting like this by Noor, Parrish, Schramm, and Sheffield. But I just want to point out that basically, if you want to now prove some subdiffusive speed estimate for the random walk on the graph, then you know the random walk is, say, at most diffusive in the omega metric. Okay, so now you should give, you should try to find a metric where the omega metric is much bigger, say by some power, than the graph distance. And then the fact that it's at most diffusive in the omega metric will tell you that it's subdiffusive in the graph metric. So it's simple, you know. And of course, by the way, I mean, you can't just take this to be arbitrarily large. The weight is normalized in L2. So like there is a competing constraint there. Okay, so let's talk about what happens, say, in this in large percolation clusters in critical percolation on the square lattice. So what I mean by large is that in some sense that Keston made precise, you condition on being in an infinite cluster. You have to make that precise, but or you can just think about do percolation with bond percolation with probability half, and then just take a large cluster there and look at and then I want to look at the speed of the random walk there. So as I said before, Keston proved that the random walk is, the fusion is anomalous in this in the Euclidean metric. So it's at most diffusive or it's subdiffusive in the Euclidean metric. And on the other hand, it's not exactly clear what this theorem states. You have to state in the correct way, but it's known that, as Smirnov was mentioning before, that the geometry here is very fractal, and path distances tend to be bigger than the corresponding Euclidean distances by some power. Which means that, again, which means that from Keston's theorem, you don't get subdiffusivity in the graph distance. So here's a result with Shishendu that you can get subdiffusivity in the graph distance here. Okay, so like the random walk is in fact subdiffusive in the intrinsic metric. Okay, and let's just talk about how to do it. Let me remind you, what we want is to find one of the, this weight omega such that, okay, we have this upper bound constraint. We can't have more, the area has to be at most 1, and we want it to be larger than the graph metric. And in fact, let's say that we want this to hold for every x and y. This omega metric is larger than the graph metric by some power bigger than 1. Okay, I'll show you. Let me just show you the picture now. So here's what you do. It's well known. It follows from the sort of computation of or bounds on the 1-arm and 2-arm exponents of critical percolation, that if you take some bounding box and intersect it with a percolation cluster, you can define this thing called the backbone, which is this. This is obviously a horrible color choices here, but I'm having trouble to see which is which now. But this orange thing is the backbone. It's a set of points that have 2 disjoint paths to the boundary. And what the arm exponents tell you is that if you take large percolation clusters and intersect them with a large box and define this backbone, then most of the mass, most of the vertices sit in these bushes that off of the backbone. They sit in these non-orange pieces. So now you can see, if you want to put weights on the vertices but be economical and still get the distances to be very large, then it makes sense that you should put weights on this backbone, because actually if you partition the plane into squares of this size, then in order to move a long distance, you will have to move along these backbones. So I'm saying that all of your movement at a given scale will have to be on this asymptotically vanishingly small set of vertices. So you put the weight there. Of course, the backbone was only defined with respect to a particular scale, so you do it at every scale. You want it to be unimodular, so you take a randomly shifted partition. But this combined with what we said before, it gives you this this subdiffusivity in the graph distance. Okay, I mean, I think and I hope it's clear that that from this this weight is not like a particularly special. It's just something ad hoc. There are pros and cons to that, but one of the pros is that you can, it's easier to use it. Okay, so I mean, we've seen now settings where these unimodular changes of metric give the ability to. Oh, I see. That's I changed the order of things. I forgot. So we're not there yet. This was meant to say that, okay, that takes care, that's one side of things. What about these random triangulations? What about the speed there? Okay, so Wow, that's, okay, this is too many symbols for this early in the morning. So let me just say that, one feature that these random triangulations had that we said is that the growth is like 4-dimensional, but these graphs have very small separators. And you could hope that, you might expect that, for instance, whenever this isoperimetric dimension, the size of the separators, disagrees, say, with the rate of volume growth, then the walk is subdiffusive, because if you think about it, it means that maybe there are all these little corners that the walk gets trapped in before it can escape to infinity. And you can prove such a thing. So let me just state it in the planar case. So if you have a unimodular random planar graph with growth rate r to the d, then this speed is at most n to the 1 over max 2 at d minus 1. And this theorem is, so this says, for instance, that as the rate of growth becomes larger and larger, the random walk becomes subdiffusive, almost surely. So that's nice. But it's off by a little bit, because it actually says that to get subdiffusivity, you need the growth rate to be like 3 plus epsilon. Being just bigger than 2 doesn't suffice. And again, in fact, this is, we didn't understand this at first, this is necessary. There are constructions where the growth is 3-dimensional, but the random walk still has diffusive speed. So okay, so in a second we'll come back to this. But how does this play out for UIPT, for these random triangulations? If you just apply the volume growth, because you have 1 over d minus 1, it says that the speed is at most n to the 1/3. That's what we said on the previous slide. That was previously known, okay, not for UIPT, but for the quadrangulation version from a paper of Benyamini and Corian. Although here you can see that it just follows from planarity, unimodularity, and volume growth. You don't need any additional structure. One funny thing is that when I presented this theorem at Russ Lyon's 60th birthday, Nicolas, bristled a bit at this and said, we only stopped at 1/3 because that's a nice number. We could have gone further than 1/3. And indeed, he, shortly thereafter, deposed a preprint where, you can get some slightly better than 1/3 in a variety of models, in particular in UIPT. But then shortly after that, actually, Gwynn and Hutchcroft, I have a problem with the G and H. That is the correct alphabetical ordering. Yeah, I have to sing the whole thing to get there. They proved that actually the speed is at most n to the 1/4, which is the conjectured bound. It's the one that follows from these sort of Einstein relations that predict the speed in terms of the growth rate and the spectral dimension. And let me say that Jason will talk about Louisville quantum gravity later in the afternoon. Their approach is to define one of these unimodular random weights, but with the weight coming through a coupling to these mated continuous random trees, which are then coupled to, which have a geometric representation coming from Louisville quantum gravity. But this is nice. The point is being that, even in these specific situations, you can, by the way, let me say why is this kind of setting of random weights useful there? And it's because this coupling, if you look, the more precisely you want to look at it, there's some kind of uncertainty principle, the less precise the statements are. And these weights allow you to pull back some geometric information in this kind of coarse way. And sort of essentially simultaneously, Gwynn and Miller showed that this is the tight rate of escape. So now, for instance, we know that the rate of speed for UIPT is n to the 1/4. Okay, so I'm going to now end with two open questions, which are, they both cut across fields to some extent, which is the kind of thing that I think is pretty cool. And they address some of what's going on here. So So we know what's happening for random triangulations, but not for random quadrangulations. And that's because, again, the triangulations are studied through this very precise coupling that doesn't exist in its present form for, say, random quadrangulations. Those couplings were sort of brought to light, studied in this paper of Gwyn, Holden, and Sun. But we also know, that if you just have unimodularity, planarity, and uniform volume growth, it doesn't suffice to get the kind of conclusions you want, say, for UIPQ or for a number of other models. So let me give you a picture of what these things. So here is sort of this gives you a planar graph which is the dual of the graph drawn here. So the vertices are the cells, and two vertices are adjacent if the cells are adjacent. And this graph has the property that the random walk spreads out in this highly non-symmetric way. And the first question I would ask here is it possible? Is it possible to kill this with some nice assumption? Okay, because like I said, even if to establish that nice assumption, you have to go through a very complicated coupling. It would be nice to somehow be able to make an assumption that rules this out, and then be able to recover the desired conclusions. Not just because it would work for these other models, but because it's not clear what the so one thing that I remember seeing a long time ago in a paper of Smirnov is this is that this idea that sort of random geometries can often, because you have these fluctuations, you can often do things you can't do with sort of deterministic geometries. Like basically the fluctuations allow you to fit more stuff, more weirdness in there. It would be very interesting to know how rigid this sort of space of, say, unimodular planar graphs of uniform volume growth are. And it's at least morally, and it seems maybe more than morally, connected to this very well-known conjecture from geometric group theory, Cannon's conjecture, which asserts that if you have a Gromov hyperbolic group and its Gromov boundary is topologically a two-sphere. So here I drew a sort of, this is so let's say a picture of the hyperbolic plane in the Poincare disk model. The boundary is a circle. Now think about three-dimensional hyperbolic space where the boundary is a two-sphere. If you take any hyperbolic group where the boundary is a two-sphere, then Cannon's conjecture, which is a sort of a strengthening of Thurston's hyperbolization conjecture, which is now known to be true by Perelman's work, but this is still open and quite a beautiful question. It basically says that you look at the boundary, you take a sequence of planar graph approximations to the boundary, and then the question is it always the case? Okay, you can't see that this here, but is it always the case that there exists a nested tiling of this sequence of approximations, meaning that basically you take a tile and then you refine it, and then you refine and refine, and each of those tilings is a tendency or approximate tendency graph of the GNs where the cells don't degenerate. By the way, I'm mentioning it's related because if you take the finite volume limit of this thing, if you keep rescaling and say take a Gromov-Hausdorff limit, then you can easily show that, the sort of like the fact that these cells have their aspect ratio becoming more and more elongated, that has to happen. And so the question there is is it always the case that basically if you have a lot of symmetry, okay, so it's not clear, but this group acts on this space by quasi-conformal maps in a very nice way. If you have a lot of symmetry, is the space of possible geometric structures rigid in the sense that there are only things that are conformal to the standard two-sphere? It's at least morally, there's a very nice drawing, I mean, there's a very nice arrow from sort of trying to give some coarse notion of symmetry that would allow you to recover the correct exponents you want, and this setting here, where, for instance, I mean, work of Bonk and Kleiner shows that you can do an intrinsic version of this, where you instead of tiling in the plane, you can just talk about effective resistance estimates in these graphs. Well, if nobody, I learned about this possible connection from Asaf Nachmias a few years ago, and I encourage people who think about this to look at it because it's quite beautiful and somewhat related. Let me now mention finally, in the last 2 minutes, a relationship coming from theoretical computer science. So there is a well-studied conjecture in graph theory called the planar multiflow conjecture. It's basically that people perhaps know the Max-Flow-Min-Cut theorem. If you don't just have a single ST pair, you're sending flow from S to T, but you have multiple SI-TI pairs, then you can think about what's called a multi-commodity Max-Flow-Min-Cut theorem, and it's conjectured that in planar graphs you have such a multi-commodity Max-Flow-Min-Cut theorem. It's known that in expander graphs you don't, but it's conjectured for planar graphs. It's equivalent to the assertion that on every infinite planar graph, the path metric admits a Biley-Schütz embedding into L1. So an embedding into L1 that preserves distances up to a constant factor. Here's my question, so this is the first problem I started thinking about as a grad student. Sadly, I spent way too much, this first thing here, way too much time trying to prove it. If there is a counterexample, it has to look very much like UIPT. So you can ask, and now I'm phrasing it to experts in the room, is it possible that this conjecture is false for, say, the Brownian map? And in fact, actually, it's most natural to do this in the setting of Louisville quantum gravity. I mean, I think then there maybe the metric is easiest to work with. And let me just say that I will even sketch it for any experts in the room how the proof should go. Basically, there is a line of reasoning here that goes back to works of Chigger and Kleiner about reasoning about L1 and embeddings in terms of sort of understanding the local structure of sets of finite perimeter in an underlying metric space. And so if you could classify, for instance, in the Brownian map, all the sets of finite perimeter. For instance, so what I mean by, so like you can imagine here, this has this very fractal structure. So you could take a set, and you could say, if this set intersects these little tendrils, these baby universes at every scale, then maybe if a set intersects infinitely many scales in this non-trivial way, that set cannot have finite perimeter. So if you could prove that, you would disprove this conjecture. You first have to state it in a way that makes sense. But I guess I'll just leave you with the fact that, there are all these beautiful connections in the world, even between the Brownian map and possibly, theoretical computer science. Yeah. So let me end with that. Thank you.
So we have time for a question or two.
So you say that you would prove this by saying that a set of finite perimeters can only interact non-trivially with finitely many scales, but like how does this lead to the statement that it can't be embedded into L1?
So an L1 embedding is equivalent of a metric space is equivalent to saying that you can foliate it by cuts so that the distance between a pair of points is proportional to the measure of cuts that separate that pair of points. So if you could say that, it would basically mean that a given cut can only handle separation of pairs at finitely many scales, and that would imply that essentially there's no Biley-Schütz embedding because just by looking at a geodesic between 2 points, as long as geodesics have to use in a non-trivial way all of the scales, then you can think about how an L1 embedding of a geodesic looks like. It's sort of a sequence of cuts, parameterized by time along a geodesic. In fact, there's some rigidity property that every L1 embedding of a geodesic has to look like that. So if a geodesic interacts with, say, infinitely many scales, then basically a bi-Lipschitz embedding restricted to that geodesic would have to have the same property, and the cuts that occur in the support of any Lipschitz L1 embedding have to have finite perimeter. So if you combine those two things together, it's look, I've actually drafted an email to you and Jason a number of times, but have failed to complete the email because I don't exactly know how to state it. So that's the best I can do.